It conducts only for 180 degree of the input cycle. So if you provide a full sine wave input, one piece of class B amplifier will output only for 180 degree of the phase. In order to get a 360 degree output across any given load, it is necessary to use two class B amplifiers. On the first half cycle, one of the class B is on. During the second half cycle, the second class B is on. There is an error on this slide and on some of the upcoming slides. This slide says NPN provides the negative half, PNP provides the positive half. That is not necessarily the case. You can have both of them NPN transistors, which will provide you each half of the input cycle. The time when we use two different types, NPN and PNP, it's a special type of connection. It's called complementary symmetry, which we will not be studying. So you may correct this one. The equations for class A amplifier and class B amplifier are totally different. When you are asked any problem in the quiz or exam, you have to carefully look what is the type of amplifier, which class it is, and what type of connection. Based on that, you have to pick the correct equation. Equations will be always there in the formula sheet, but whether or not you get it correct is the ability to understand which one to pick. So for the input power, we always define input power as DC power. It is coming from the DC source, VCC multiplied by I DC, the DC level current. Sometimes the DC current is not directly given. So we can find the peak current using peak voltage divided by load resistor, Vp divided by RL. You're going to get the peak current. And IDC is 2 over pi multiplied by peak current I of P. Hence, the input power equation may become in this format. VCC multiplied by 2 over pi multiplied by I peak. We'll do a few examples today where you will see that you can manipulate the equation in so many ways in order to come up with a solution. For the output power, we define output power as the AC power. It is load voltage square in RMS divided by load resistor. You know the general equation of power is V square over R. So if you take the load voltage RMS square divided by the load resistor, you can have the output power. What is the efficiency then? Output divided by input multiplied by 100, and then you have the percent sign. But this equation is very simplistic. The examples we do not use simple equations. Here on the next slide, you will see there are how many ways, so many ways of writing one equation. Begin with the first one, the output power AC. It says load voltage RMS square divided by load resistor. But what is RMS? RMS is peak divided by root 2. So if you are given, or if you somehow find the peak voltage, you can take peak over root 2 squared. This thing becomes peak load voltage square divided by 2, because you are squaring the square root of 2. And of course there's an RL in the denominator. You can even express in terms of peak to peak. RMS equals peak to peak divided by 2 times root 2. Now square that, you'll get VL squared peak to peak over 8. If you take a square of 2 root 2, you get 8. 4 times 2, 8. So in peak to peak terms, it becomes VL squared peak to peak over 8 times RL. See, there are so many variations. In a class B amplifier, it will reach the maximum efficiency when the peak load voltage across the load resistor is same as the input DC bias voltage VCC. It's possible. If load voltage is a full amount of the VCC, you'll get maximum efficiency. What is the maximum efficiency of class B amplifier? From the table, you may see it is 78.5%. When VL equals VCC, VL peak equals VCC, it will be 78.5% max, not more than that. And also output equation, you know, peak voltage square over 2 RL. Now replace VL peak with VCC in the equation. You can also express in terms of this VCC square over 2 RL. The input power we know, it's a DC power, VCC times IDC. We also know from the previous slide, what is IDC? 2 over pi times peak current IP. Further developing the equation, we have VCC 2 over pi. What is peak current? Peak current is peak voltage divided by resistance, Ohm's law. And peak voltage here equals VCC. So in this equation, you can write VCC over RL. You are multiplying with another VCC, it becomes 2 times V squared CC over pi RL. If you want to find the maximum percent efficiency, if you are given VCC and VL peak, how would we write this equation? For the output side, you can write output is VL square peak divided by 2 RL, and you divide it by input power PIDC. Now instead of VCC over RL, you can write instead of 2 V square CC over pi RL, you will not find that solution. You should write VCC times 2 over pi times VL peak divided by RL. You are going to get an equation, percentage equation in terms of VL peak and VCC. I'll bring you to the whiteboard for that. Let's go to class notebook. Maybe not whiteboard, just do a class notebook. While it's loading, we have to wait a bit. Okay, for collaboration space, I'm gonna add a new page. Is everyone ready? Is everyone ready?
Yes.
Yes, sir. Ready.
Percent efficiency, I'm just doing a freehand drawing. Typing is kind of hard. P out of AC, and then input power. It looks like rho. My drawing looks like rho. It's not rho, it's P. My hand is just a bit slanted. Okay, let's draw this. P out AC, trying to remember the equation. VL square peak, I think, divided VL peak square divided by 2 times RL. That's the equation. So I'll write here VL. And remember, this one is multiplied by 100. So let me correct that one. This equation has to multiply by 100. So equals this. And then we have the load voltage, peak load voltage square over 2 times RL. I hope that is correct. And input DC power, we said it is VCC times IDC, right? And IDC is, what was IDC? 2 over pi times I peak, and I peak equals V peak divided by RL, VL peak divided by RL. So I might write VCC IDC. I'll write first and then I will erase just to show you the steps. IDC equals what? I peak times 2 over pi. This is the one, right? And then I peak equals V load voltage peak divided by RL. So I replace I peak with VL peak here, V load voltage peak. I hope you understand the step. It is Ohm's law divided by RL. Now simplify the equation. What is going to happen? There's a VLP square on top. There's one VL peak in the bottom, so it will cancel out one time, leaving you with just one VL peak. And then you have denominator RL, 1 over RL and 1 over RL. You're dividing them. The RL term gets cancelled out. What do we have? Pi goes on top and then multiplied by V of LP, 1 over 2, and then divided by 2, you have 1 over 4. The equation is reduced to this format. If you do it properly, it is 1 over 4, and then you will get VLP, the peak voltage, divided by VCC, and then something divided by 1 over pi. Pi goes on top. Pi will go on top, multiplied by 100. This becomes 100 pi over 4 times VLP divided by VCC. What is the numerical value? From my calculator, the numeric value is like this, 78.54. This is percent efficiency. This is already converted in percent. 78.54 multiplied by this ratio. V load voltage peak divided by VCC. Now you can see the relationship. If the load voltage, the peak voltage is same as VCC, what is your percent efficiency? VLP equals VCC. What is the percent efficiency?
78.54%.
And that is the max. You obviously you cannot go more than VCC. So this is the maximum percentage efficiency you can get out of a Class B power amplifier by setting your peak voltage equal to VCC. If the peak voltage is less than VCC, you'll get a fraction of it. Let's say it's half of VCC, so you'll get about 38%, 38, 39%. So the lower your peak voltage is in relation to VCC, the lower your efficiency will become. This derivation is not done on the lecture slide. It is done somewhere in the textbook. In some problem, this equation, this whole equation, this is actually an equation. It is useful for some problem. We'll go back to the lecture slide. Here, so it provides you a question mark here. Percent efficiency, how much? We just came up with the equation, 78.54 times VLP over VCC. You can note it down for yourself. And also remember in how many ways you can actually manipulate the equation. The maximum efficiency of the Class B amplifier will occur when the maximum peak load voltage reaches the same level as VCC. Any questions?
Don't have any question.
Don't have questions, okay?
Teacher,
Yes.
the note that you wrote down, it is still in there, right?
Yes, I don't erase it. It will be in the class notebook. You just have to find under the collaboration space and you can have a look at it. I did not erase anything. It is saved there. Again, to recap, for Class B, maximum power to load VL peak equals VCC. So the maximum output power is VLP square over 2RL. If you write VCC square over 2RL, you can come up with one equation. Then the peak current is VLP over RL, means VCC over RL. IDC max is I peak times 2 over pi. So now it becomes 2 VCC over pi RL. That is correct. Maximum input power, when you have maximum IDC, it will be VCC times 2 VCC over pi RL, just like this, 2 VCC square over pi RL. You can just use, instead of VL peak in the output power, you can just use VCC square over 2 RL. All the VCC will cancel out. You will get pi over 4 multiplied by 100, 78.54%. But for general cases, if you want to find efficiency, general cases, you can take 78.54 times VL peak over VCC, just like I did in the note. Now we will look at 3 examples first involving the Class B power amplifier. Let's focus on example number 7. I'll bring it on the screen in the class notebook and I will ask 3 students. There are 3 parts of this problem. Again, I start rotating, so I'll start asking again after midterm. Is Balang here? Mr. Balang?
Yes, sir.
Okay, Balang will find the input power. How about Mr. Thirawut present?
Yes, Kap.
Thirawut will calculate output power, and Napatra, Mr. Napatra present?
Yes.
Circuit efficiency. Let us Let me see if I can copy paste this thing. No. I'll bring you to the class notebook. Can I take a screenshot? I should take a screenshot. Hold on. 1, 2, 3. Snapshot is taken. It will now be transferred to the class notebook. And I'll open the class notebook page for you again. Just let me bring it in. Power amp example 7 is the name of the problem. Can you still hear me? I'm getting message bad network quality.
Yes, we can hear you.
It was hard to log in today, actually. Okay, class B, what are the information being given? I can write it for you. 20 volt peak signal. So that is our VL peak. 20 volts. The load is 16 ohm. It's a speaker. RL is 16 ohm. And then you have VCC is 30 volts. Let's start with determining the input power. What is the equation for input power, Malan? PI DC
equal VC over
VCC. VCC over, no, VCC times IDC. And what is IDC? IDC equals 2 over pi times I peak. So you can find out the rest. We will wait. 2 over pi. From the information given, you can find the peak I current. What is peak I current? Peak voltage over load, Ohm's law.
Yes, 30 times.
Okay, so 30 times 2 over pi multiplied by what? What will you write in the place of IP? 30 2 over pi. Tell me, what is IP formula? Using Ohm's law, what is IP? You can also look at your slide.
It's BL, right? BLP
VLP
over
divided
RC?
by RL.
Oh, IL, okay.
So 20 IL peak is this. Ohm's law, simple Ohm's law. 20 volts peak divided by 16 ohm is your peak current IP. This one comes to, what is the value? What is the value of input power?
10.12.
Is that correct? 60 times 20, 1200 divided by pi, about less than 400, and then divided by 16. It is just over 20 something watt. What is the actual value?
23.87.
23.87 watts. we can write 23.9 watts. That will be okay. Input power. Mr. Thirawut is doing the output power part. What is the output power for Class B amplifier? You can look at your own slide. I posted it. It is B square CC divided by, no, that is for maximum efficiency. We cannot just say yet that it is maximum efficiency or not, right? What does the slide say? Output power is VL peak square over 2RL. I think that's the equation we have to use. We did not say that it is operating at maximum. Also, you can see the peak voltage load is not same as the VCC, so obviously it is not maximum. What is the equation then? VL peak squared divided by RL. If you take RMS, it's VL squared divided by RL, but if you take peak, it will be VL peak squared divided by 2RL. Find out the value. 20 square is 400 divided by 2 times 16. 400 over 32.
12.5 วัตต์ครับ
12.5 watts. Mr. Napatra, what is the efficiency? You have the easiest part to do. What is percent efficiency?
Uh, 52.3%.
All right, let's do output power is 12.5. It comes from output over input power and multiply by the 100. 23.9 is almost 24, and then you can see it's just over 12. It's just over 50%. 23.9. And then 100. If you take this equation, it comes to 52.3%. That's the efficiency of this Class B amplifier. 52.3%. If you make this peak signal same as VCC, you'll get 78.54. We have another problem. It is called example 12.8. This will be another group of students which I'll call. So for those three, thank you for your participation. And let me copy paste it from the slide. Take a snapshot. Let me just expand. There are three things that the question is asking: maximum input power, output power, and transistor dissipation. Is Pakon present? Pakon?
Yes.
For you will be maximum input power. Rajay?
Yes, Sajed.
The Rajay output power, the next person on the list, Miss Johnny Khan. Is Johnny Khan present? Not present? Miss Johnny Khan, can you hear us? Okay, I'll put her in another problem. Michelle? Is Michelle present?
Yes, Ajahn.
Michelle, you'll do the last part, transistor dissipation. Dissipation means how much power is lost in terms of heat. And I'll guide you along the way. Maximum input power, so Pi max equals what? What is the general equation of input power? VCC times IDC. IDC max. Now we have to write IDC max. And maximum IDC happens, or when does it happen? Maximum IDC. When the peak voltage is same as VCC. So you can write like this. Pakon, are you following? Are you doing?
Yes.
2 over pi. I peak is VL peak divided by RL. And in the case of maximum, VL peak is same as VCC. So instead of IP, let me cancel out. I will write VL peak over RL. And instead of VL peak, the maximum occurs when VL peak equals VCC. Your input power equation becomes 2 VCC squared over pi RL. Let's find out that one. How many watts?
35.
Exactly?
5.
35 point how much? I got 35.81.
5.8.
35.809. I want to write 35.81 watts. The second part is given to Rajay, Mr. Rajay. P out,
Yes.
max P out. Thinking, what I'm thinking, I'm not looking at the slide. VL peak square over 2RL, so VCC square over 2RL, right? P out max. This is the equation for output power. If you take in RMS, it's load voltage square over RL, but now peak is given. You can say VL peak square. Looks ridiculous. I should decrease it. VL, oh, where did it go? VL peak square over 2RL. When do you get the maximum power? For class B, when VL peak is same as VCC, so we can write VCC squared. I'm showing you all the steps so that you understand. Now you can find the maximum output power.
Yes, Ajahn.
What is the value?
Like I got 28.13.
28.13 watt. Okay, we'll take that answer.
Yes, what?
Just out of curiosity, I want to calculate the efficiency. So what is the efficiency? You know, you can take the ratio 28.13 over
We
VCC
power
28.
outage like power input.
and multiply by 78.54.
I
No.
got like 78.5. The efficiency?
Oh yes, because it's output power over input power, right? Because if I take as a ratio, I have to take VLP over VCC. VLP is same as VCC. We have already established that it is maximum. We're using that case, so it's 78.54. But if you take 28.13 over 35.81, I also see 78.5% efficiency. Michelle, your turn. Power dissipation, let's call it PD. What is power dissipation in this circuit?
Maximum P20 2.
There's actually a formula for this.
Yes.
Maximum P2Q. Because there are two transistors, not one. Class B amplifier, there are two. There's a maximum P2Q formula which is not on the slide. Let me write it for you. It is 2 VCC square over pi square RL. Hold on, I'll just do it here. There's a formula. I don't think it's also on the formula sheet. P2Q. When a class B amplifier operates in push-pull, there are 2Q. P2Q is 2 VCC square. So it's like this. 2 VCC square divided by pi square RL. Pi square RL. Transistor dissipation. When you drive a load with a class B amplifier, you don't want the load to have one cycle off, another cycle on. We're assuming that two transistors are running. So if you take this formula, 2 VCC square over pi square RL, you get the power, the heat loss for two transistors. But if you divide this by 2, you get the heat loss in each transistor. So what's the value then? 2 times 30 square, 900 times 2, 1800 divided by 16 divided by pi. Am I doing the right thing? Pi square. Oh, okay, not pi square. 1800 divided by 16 divided by pi squared. 2 transistor dissipation is about 11.4 watts. So you divide by 2, you get 5.7 watt. Under maximum condition, in a pair of transistor, each will be handling about 5.7 watt dissipation.
Teacher,
Yes,
what are we finding? Transistor?
we are finding transistor dissipation, the power that is lost in terms of heat. So here's a formula. I should add this formula in the formula sheet for your final. Power dissipation. This is the power loss in 2 transistor. If you take 2 times 30 squared divided by pi squared times 16, you will get 11.4, 11.399. So for 1 transistor is half of that. Michelle, did you find the answer finally?
5.7 ค่ะ
So 1 transistor for each transistor means it is implied that there is a pair of B, class B. Only 1 class B is useless. You can't do anything. Is this one divided by 2? $5.7 watt should be the answer. Exact is 5.69. I got 5.7 watt. So
Is the formula in that?
the
Is the
formula
formula in the lecture?
it's not in the lecture slide. Please
okay.
remind me to provide this in the equation sheet.
Okay.
I should try to draw this on the lecture slide, but I'll keep this thing here. It is from the textbook. Actually, not everything from the textbook came in on the lecture slide. There's an equation called equation 12.28. You can also derive it, but just remembering the equation is fine. You don't even have to remember if it's in the formula sheet. This problem tells that under maximum condition, a pair of transistor each is handling 5.7 watt, meaning that, you know, when you turn on a transistor, there's a PZ max, power dissipation. So at this moment, they are handling 5.7 watt heat. It is not being used for anything. And at most, they can deliver 28.13 watt to this load, but it is drawing 35.8 watt from the supply. We'll do one more example, which is related to the ratio equation I derived a while ago in today's class. This is example 12.9. And as usual, I'm going to take a snapshot, screenshot, and paste it on the screen. There will be 2 persons because it has part A and part B. Let it load. Miss Chonikan, are you present? Can you hear us or not? That's the question. Is Chonikan present? I see on the list of students. Phil, are you present?
Yes, sir, I'm here.
Yeah, let me ask Chonikan one more time. Just sending a message. If Chonikan doesn't respond, Miss Silicon will be another participant.
Yes, teacher.
Okay, let's go ahead. Phil and Silicon. Phil, for Phil, we have this example 12.9. It's a kind of dark background. Hopefully you can see it. There's a class B amplifier with the supply voltage VCC 24, and VL peak is given in two cases. For case 1, please find out the efficiency, and case B will be Miss Silicon. Remember the equation which relates the maximum efficiency with the ratio.
For A, I got 72.0%.
That seems about right. How about for B, Miss Silicon? She's working.
For B, I got 20% here.
Is it 20%? Okay.
Yeah.
6 over 24 and then multiply by 78.54. 19.6 for 20. This is the equation that you can use as a shortcut. Percent equals this. Point 5. I'm not writing the second digit. So the ratio of the first one, 22 over 24, you multiply by 78.5. If I multiply by 78.54, what will happen? 71.995, so around 72%. A is approximately 72%. For case B, let's take the ratio. 6 over 24 times 78.54, 19.6, you can say approximately 20%. If you wrote 20, if you wrote 19.6 is okay. If you wrote about 20%, still all right. These are the main examples involving the Class B amplifier. You can have even more. We will now look at a few, maybe 1 or 2 examples. Just one. For Class B, how you can make the Class B happen. And I'll point out some mistakes to you again on the slide. Transformer coupled push-pull Class B. There is a transformer. You have primary side, primary coil. This is side 1, I should say 1. Primary side, secondary side. You have an input signal, which is an AC. You know this connection from your diode application. This is called center tapping. When you center tap a transformer coil, it will split the incoming signal into 2 parts. One half cycle becomes 2, one input becomes split into 2 half cycles. Both of the transformers are NPN. As you see, the arrow of the emitter going out. I'll say NPN. Both of them are the same. And then you connect with the load again. This connection is called transformer coupled push-pull. Why the name push-pull class B? One transistor pushes the output voltage up, which means you are going to get the positive output during one of the half cycle. The other one pulls down from the zero level, means you are going to get the negative side of the half cycle using the other transistor. On the output side, when you have center tapping again, it will combine the two halves of the AC waveform together, and then you will have a full waveform again. So from one transistor you may get something like this. For the other transistor you are getting this. Two of them combined at the end using center tapping. The load is given continuously. If you have only one class B, it will be only on, off, on, off. It can get very annoying, and it's not very useful too. If you have an application that needs continuous power delivery, you should have two class B push amplifiers. This one describes the operation. Here is where we have the mistake. Where is the mistake? This is the mistake I'm highlighting. Q2 is also NPN. There's one type of connection where you can use one as a PNP and the other one is NPN, but that is not called transformer coupled push-pull. That is called complementary symmetry operation, which is not, I did not include it in the course outline, so I will not teach that one. Please correct this mistake. What happens during the positive half cycle? Transistor Q1 is on. It is on, conducting. Transistor Q2 is off. So I'll just put the cross sign. During the second half cycle, transistor Q1 is off. Transistor Q2 is on. When you combine them, you are going to get a full 360-degree cycle of the output. Most of the problem involving the Class B amplifier over the past many semesters, they come in form of this, usually without picture but some sort of description. And most of the Class A amplifier which was asked in the past, they come in pictorial form. You are given a circuit, maybe a big one like 12.4 for example, or a small one using a series FET, and it's in that form. For power amplifier, we are more concerned with efficiency. So most of the calculation involves some sort of efficiency calculation and power dissipation whenever it's applicable. Any question on these two types of amplifier?
The highlight one we have to change, right, Ajahn?
Yes, the highlight one, please change it.
Change to
From the
P2.
symbol, yes, change to NPN. From the symbol, it's very symbol, it's obvious, it's NPN. If it was PNP, the arrow will go inside the body of the transistor, but it is not. When you have a Class B amplifier, you can experience something, a strange phenomenon known as crossover distortion. Remember, there are two transistors involved, Q1 and Q2. Transistor 1 is, we call Q1, and we are calling the second transistor Q2. If they do not turn on and off exactly same time, you have a gap in the output. What is your desired output? Let me try to draw. The desired output will be like this. Transistor Q1 on, you have an output. At this moment, Q1 is off, Q2 must turn on, and then you get the second half cycle. But if there is a gap, the turning on and off is not properly time synchronized. This is what is going to happen. Q1 is on, okay? At this moment, Q1 turns off, but Q2 does not turn on immediately. There is a time delay, maybe millisecond, nano or microsecond, but there's a time delay. During this delay, there is no output, and then Q2 turns on. Instead of getting a sine wave, you are getting a wave in the shape of this black wave. It does not maintain the pure form of a sine wave. It gets distorted, it gets corrupted. We call it distorted waveform. And this phenomenon is known as distortion. Specifically, we call it crossover distortion. Why crossover distortion? Because the voltage is crossing over from one level to the other level. Where is the crossover point? The crossover point is the horizontal line. It is V equals 0. That's the point. So from a positive side, when you try to cross over to the negative side, when you try to move to the negative side, you are crossing over. And from the negative side, you try to come back to the positive side, you are crossing over to the other peak. And this distortion happens during the crossing. If the two are not properly synced to turn on and off. Let's assume that Q1 is also delaying. What will be the waveform? It will be like this. It will continue. But if Q1 turns on properly, it will go as a sine wave, and Q2 is faulty, you will get another distorted. In this chapter, we talked about two types of distortion. The first one being the crossover distortion. This one is another type of amplifier. Just for your knowledge, we don't solve problem with this, but just for your knowledge. See what is happening. It is called quasi-complementary push-pull amplifier. And the one which will use one NPN and another PNP, it's called complementary symmetry. They sound very similar. One is complementary symmetry, this is quasi-complementary. But in this quasi-complementary, what do you have? You have a PNP and PN. The upper pair, you have seen this. I asked this question in the midterm exam. Do you recognize this one? It's a Darlington amplifier, Darlington connection. The beta of the transistor is beta 1 multiplied by beta 2. Very high current gain. And this one is not, it is not, you see, it's not Darlington. The output is fed back to the input side. This is a feedback connection. Look at the direction of the arrows. That's why you have to use two different types. This one is definitely Darlington. This one is called a feedback. We have a whole chapter on feedback and oscillating circuit later on before the final. If you join a Darlington pair and a feedback pair, it can also perform push-pull operation. It will increase the output power ability as well because the Darlington has a very high current gain. The current is multiplied by 2 betas. The input current will get multiplied by beta 1 and beta 2, and you see you are getting the output at this point. There's no problem to solve from this quasi-complementary. Now we talked about crossover distortion. There is a general case of distortion. What did I tell you about distortion? What is the meaning of distortion? It means the signal shape is twisted, distorted, corrupted. The general statement goes like this. If the output of your amplifier, if the output signal is not a true replication, true representation of your input signal, then you can say your signal is distorted, which means the amplifier behavior is not linear. Linear behavior is usually a concern in the small signal amplifier, but also you cannot ignore it in the case of large voltage and current. There's an analysis technique known as Fourier analysis, Fourier transform. It transforms the time domain signal into a frequency domain analysis. But we will not do that. It's a matter of engineering mathematics class. But what we get from a Fourier analysis is if you have a distorted waveform which is periodic, means it has a regular period of oscillation. For example, a sine wave or a cosine wave. It can be broken down into individual frequency components. Like I said, the Fourier analysis, if you do Fourier transform on a time-varying signal, it will show you a frequency, amplitude versus frequency. It will show you the dominant frequency. So doing the Fourier analysis, you can break down the corrupted signal into so many different frequency components, and the small components are called harmonics of the fundamental frequency. What is fundamental frequency? Fundamental frequency is the main frequency that you are expecting. Let's say you have sine omega t, omega is 2 pi f. Let's say frequency is, what should I say? 1 kilohertz. Let's say the f equals 1 kilohertz. If the output signal is not corrupted, the output signal frequency will also be 1 kilohertz. But if it's corrupted, it will have small components which are called harmonics inside the output signal. And these harmonics are integer multiples of the main frequency. So you'll have in the distorted waveform, you will have 1 kilohertz, you will have 2, 3, 4, 5 integer multiples. We call it harmonics. When you combine, you'll get a very strange waveform. This is the explanation of harmonics on slide 30. Let's say you have 5 kilohertz fundamental frequency. The first harmonic, I don't think it should call it the first harmonic. In my opinion, is your basic frequency. So the basic is 5 kilohertz. The second harmonic frequency is 10, 2 times 5, third is 15, fourth is 20, and so on. The first, third, fifth, seventh, ninth, those will be called the odd harmonics because that's the multiply of odd number. Second, fourth, sixth, 8, 10, 12, etc. Those will be called even harmonics. Picture now, what is the meaning of harmonic distortion? Focus on this one. Okay, let me trace this one. V1 sine omega t. This is your main component. Omega equals 2 times pi times f. Everyone remembers that? The formula for omega? 2 pi f. Distorted signal. So there's a second harmonic coming in. It became, inside the cosine, it became 2 omega t. Not only omega t, it becomes 2 omega t. This is the second harmonic. Frequency has increased. You see, the waves are spaced more closely. When you have high frequency, you have waves are very close to each other. Third harmonics is 3 omega t. So sine, cosine, sine, it goes like that. 3 omega t now. The waveforms are getting even closer. So you have your fundamental component, The first one, the large one is B sine omega t. The second harmonic was V2 cosine omega t. The third one also embedded inside the signal. It is V3 sine 3 omega t. Second one is V2 cosine 2 omega 3. When you do all the addition, when you add everything, it does not look like a sine wave anymore. It looks like this. And then at this point, you see what's happening. This yellow one that I drew, it looks like this. Your output waveform is no longer a sine wave, which you are expecting. This is called the harmonic distortion. If a signal is not purely sinusoidal, then it contains harmonics. If you do something in the lab, try to take a signal, and then you have some noisy input. This noisy input can actually create the second, third, fourth, fifth harmonics. That's why when I taught you the op amp, the input impedance is very high. In the common mode, you should not have common mode, actually, the mode where noisy signals should get completely cancelled out, but in reality, they don't get cancelled out. But if you have a high common mode rejection ratio, you will minimize all this noisy signal. Any questions about this one? No questions?
None at the moment.
We can actually finish a bit early today because I'm going a bit too advanced compared with our schedule. Nonetheless, let's see. In the harmonic distortion, we have problems that you can be asked to calculate. It is calculated like this. Percent nth harmonic distortion is given by A sub n over A1 times 100. This is in percentage. A is the amplitude of the fundamental frequency. Let's say A1. A1 is the amplitude, fundamental frequency. A1, let's say it's 5 volt, right? An will be amplitude of the highest harmonic. So n equals 2, 3, 4, 5, 6. N does not equal 1. 1 is the fundamental. Anything above 1 is harmonics. Let's say your fundamental signal amplitude is 5 volt. The second peak, the second harmonic peak is half volt. 2.5. So what is the percent second harmonic distortion? It will be half of 100%, 50% distorted. If you have a third harmonic, which is, let's say, 1 volt, so 1/5 of the fundamental. 1 over 5 is 0.2, and then you have 20%. So the second harmonics is distorted 50%. Third harmonic distortion percentage is 20%. Usually it goes down. But you cannot add A, B, C, D like that. You cannot add percent D1, percent D2, percent D3, percent D4. The total harmonic distortion is calculated with the square root formula. Percent THD is, it should be D2, D3. Here is another mistake. This one should be D4. Square root of D2 squared, D3 squared, D4 squared, and then the whole thing multiplied by 100. 100 is outside of the square root. Is there an example? I should bring you an example. Just wait for a few moments. Content library. I'm going to the content library to find this one. Power amp. Harmonic distortion. Yes, I have an example. Let me copy that one. I can't seem to find. I just copied it and then it's gone. Oh, I have it. Let me arrange this and I'll switch the screen. Okay. Here's a one example in the textbook, and the screen switching will happen now. Example 12.13 in the textbook. Right now you are looking at it. Calculate the harmonic distortion components for an output signal. Fundamental amplitude 2.5 volts. Second harmonic is 0.25 volts. Third harmonic is 0.1. Fourth harmonic is 0.05. So basically you have to calculate percent D2, percent D3, and percent D4. Fundamental A1 is 2.5 volts, 2.5. What is percent D2 then? You take A2 over A1 times 100. Percent D2. Percent second harmonic distortion is 10%. Percent third harmonic distortion is 0.1 over 2.5 times 100, 4%. And the 4% harmonic distortion is 2%. What is the total harmonic distortion? Can we just say 10 plus 4 plus 2? No. That will be 16%. To calculate the total harmonic distortion of the signal, it is the formula square root of D2 squared plus D3 squared plus D4 squared times, I forgot this one, 100, 10.95. Now let me highlight this formula. What will you put in the value for D2, D3, D4 in the total harmonic calculation? Square root of you see is D2 squared plus D3 squared plus D4 squared. What value are you going to put?
Teacher,
Yes?
I just asked for sure. The D2, the value that I get is 1. Like 1%. The D2.
Okay, let's do it again. Point. Oh, yes, there's a mistake again. I typed wrong. It is 2.5. So let's fix that one right now. This one. Because the amplitude of the main is 2.5. .25 over 2.5 is 0.1. Multiply by 100, you get 10%. Is the rest correct?
Yes.
Yes, the rate is correct.
Okay. Now, the last equation can be a bit confusing because some students, they just take square root of 10 square plus 4 square plus 2 square and then multiply by 100. You know what are you going to get? You are just doing square root of 120 times 100. You get 1095%. That is not the correct answer. If you use this format, for D2 you have to put 0.1. 10% is 0.1. For D3 you have to put 0.04, this one will be 0.02, and then when you multiply, you get 10.95%. If you're taking square root of 10 square plus 4 square plus 2 square, you're still multiplying by 100, you're going to get 100 times more the value. So this is where you have to be careful. I'm ready to take attendance. I'll wrap it up here now. There's only a little bit left from this chapter, only 3 more slides. I had to have an explanation. Maybe I'll ask you another question. I'll create another question using a graph for the next class because we have to read the power transistor curve. So we'll stop at slide 32. And now let me take the attendance. In the next class, we can already start another new topic because this topic is finished. That's why I said in the previous class, after the midterm, the content is short. You don't always need 3 sessions. Sometimes 2 sessions, 2.5, you're done. Balang is present, Tiravut, Napatra, Pakon, Rajay present. You all did work. Michelle and Phil present. What about Chonikan?
I am ค่ะ sorry ค่ะ
I call you so many times. You sleep?
Yesterday I went to get the 3rd dose of vaccine and this day I feel really bad ค่ะ
Okay, never mind.
sorry ค่ะ
It's okay, never mind. 3rd vaccine, I don't take. I don't know what is the reaction. I already have bad reaction after 2 vaccine. That's why I am refusing anymore. Is everyone taking booster in this class? It's not compulsory, right?
I think I can. One booster.
Now they are talking about vaccine number 4. I don't know how many vaccines we have to take. 5, 6, 7.
I already got 4, sir.
You got 4?
Yes, sir. Yes.
I know someone who got number 5 or 6. I cannot tell the person's name because it's sensitive. But he is participating in some experiment by another university, so he acts as a guinea pig. Don't know if that's safe or not. Miss Siricon is present. We salute present. We salute. No response from Wisaru. Yu Cheng,
Yes, teacher.
Sesehan,
Yes, Ajahn.
Patompong,
Yeah, ครับ
Hongsu,
Yes, sir.
Martin,
Yes, sir.
Kolawit. Is Kolawit here? Not. Pichayut. Pichayut present.
Yes, I'm here to see you.
Jima,
Yes, sir, I'm here.
21,
Yes, I'm here.
Satawat,
Yes, Ajahn.
Yapeng,
Yes, I'm here.
Seni,
Yes, present.
Silipop,
Yes, Ajahn.
Pitu,
Yes, sir.
Sanan,
Yes.
Waramet,
Yes.
Nawawan,
Yes, present.
Natapop,
Yes, present.
Warapat,
Yes, present.
Nataya,
Yes, teacher.
Pichayapon,
Yes, sir, I'm here.
Pomchan,
Yes, Komshan here, sir.
Diladon,
Yes, I'm here.
Pitsanapong, Pitsanapong is present.
Yes, I'm here.
I heard you. Aditya,
Yes.
Tahsin,
Yes, teacher.
Sukaina,
Yes, teacher.
Sirin,
Yes, teacher.
Min Luin U, absent. See you next week.
อาจารย์ครับ Can you hear me?
Who?
Miss Ruth ครับ My microphone not working.
Okay, we salute.
Michelle also absent.
Yes, Michelle. Is Kolawit here? Kolawit not here today. Okay, see you next week.
Thank you, teacher.